3, 2, 1, go. And we're live. This is Retrace segment number 100 for Thursday, December 29th, 2022, 10 p.m. Eastern, 7 p.m. Pacific. Retrace is about what's going on out there. The short answer to that is computer control. See Re22. The long answer to that starts with natural, artificial, and strategic intelligence, Re79 through 81. There are the hypotheses, 1 through 11, Re17. Humanity, which is the best part, Re54. Retraces for outsiders, Re5. Outsiders are not players, Re52 to 53. Computer control is player-oriented, 54 to 55. And learning to play is what we're doing now, Re56. Okay? That's kind of getting you up to speed in the first 99 segments. What are we going to do today? I've got something special planned. Actually, I don't. We're just going to keep working. 100 is not actually significant if you're not in base 10. So, okay. Quick amendment, correction actually to Re98. I said it in Re99, but I want to say it in this one because that was a ChatGPT. The last segment on ChatGPT was 98. Alejandro gives 6 drives for AI, not 4. Go see the Re98 notes. You get all the details, but I said 4. I was just echoing somebody who said it online because I didn't bother to go look back at the original source. But anyway, the original source, no, I just put it away. But the original source is much more interesting than the echo online, of course. Okay. ChatGPT. So in 98, I said I was going, the next thing I was going to do is cross ChatGPT, the missile, actually I said the missile in 99, with the 11 hypotheses. Not going to do that today. Why? It's so disappointing. I'm disappointed too. Because I wouldn't have been able to, okay? I didn't know, and I still, let's say, don't, I didn't know what ChatGPT is or was or how it works, and so that would have been a terrible attempt. You know, it was not good. Well, now we're going to make it good with this prerequisite. We're going to talk about the architecture of ChatGPT. Okay? Is that everything? I think that's everything. Okay. So you don't need to see the boilerplate. You need to see, you do. Okay, let's start with the large. Okay, so the first and foremost, before we get to the graphic, the safest term to put on ChatGPT when you're asked, or when you're asking what is it? It's a large language model. What's a large language model? It's a language model that's large. Okay, what does that mean? Well, groping at a technical definition here, not really giving a great one, but let's say language models aim to solve. Well, first of all, okay, hang on. Just before we go into my chicken scratch notes here, you can think of a. Okay, well, start with this. So, formal languages are defined by their grammars and syntax. They're defined precisely. Okay, you can't write a Python statement incorrectly and still be understood by a Python interpreter. You can't write a statement in the C programming language and still be understood by a C compiler, unless somebody built. Well, you don't have to be. The C compiler doesn't have to. In order to be a compiler of C, it doesn't have to know what you meant by your mistakes. The grammar and the syntax define the language. We don't have that for natural language. We've been trying for it especially since Chomsky. We've been trying for years to find generative grammar and deep. What did he call it? Deep. Oh, he had a deep thing. Anyway, natural language is way more wild, way more in the woods, in the savannah, in the jungle. You can't find a set of mathematical or logical rules that easily reveal what is a sentence and what is not a sentence, what is grammatical and what is not grammatical. Okay, so what's the solution to that? Well, we just talk to each other. We just know how to do it with our brains. We have no idea really why we're all able to learn language and learn it so precisely. But if we're going to study it using machines and tools, we can use a language model. And a language model, instead of consisting of the rules of our language or our thought, to harken back to Boole, what a language model does is it takes in a lot of observation of the language, let's say in the form of websites on the internet or text conversations or whatever you have the most data, whatever you have the most of that is the language in action, that's real data that isn't constructed for some purpose, that's really naturally being used. It takes in all that as observation and it it is after that basically a way of calculating the probability of. I'm way over my skis here. A way of calculating the probability of a string or a set of words or a set of letters given a certain narrow input. It is a way of calculating what would likely be the next thing to say in an exchange, or in a conversation, or that would follow, like let's say a search, like a Google search or something like that. You can think of what it's predicting, or what it's calculating the probability of, or what it's able to calculate. It doesn't calculate the probability. It's like it's a model. It doesn't do anything without people working, operating it. But what it enables is using calculation to get from, given this input, this output. What is this output? And when we say, I think a safe way of saying what a language model does is something like, it says, based on the observations of the language that have adjusted the weights of my neural net, the nodes in my neural network, this is the most likely thing, the most likely response to this input. This output text is the most likely response to this input text, or this following text is the most likely following text to this precursor or leading text. Something like that. You can think of it as an input-output machine. It's a function. So that probability, or the capacity to calculate the probability given any input, is the model. It doesn't have like a list of all the words in the language. Actually, maybe it does have all the words, but it doesn't have all the phrases and stuff. I mean, maybe it is just the words. But anyway, the model itself is, I don't think, I don't know actually whether the probabilities are you can't because you'd have to calculate the probabilities, the probability of a given next word based on the input. The probability of this word changes based on the input. You don't know what inputs you're going to get. Okay, so think ChatGPT. ChatGPT doesn't know that I'm going to type, "Tell me your middle name." Okay, but once I do type and send that to ChatGPT, it is a logical circuit in a machine running in a container, Kubernetes container, that can take that input and calculate the probability of what. And that's the question. What? Okay, it's going to generate a response. What is that response? It's what its observation of the language has indicated would be likely. Okay, so there's a lot to. Okay, so enough. That's not ChatGPT, but that's like a language model. That's the best I can do right now. It sucks, I know. All right. Let me just read my notes. Language models aim to solve the question. Oh, okay, this is the other thing what do language models do? Like, what are they? You can't tell by the words. They solve question answering, machine translation, reading comprehension, like captioning, I think is what's meant by that, and then summarization. Okay, so when you think about a large language model, you should think the problems that it can solve are those tasks, those things that humans would do. Answer questions, translate things, translate from French to English, comprehend text, in a way that isn't just regurgitating it or shuffling the words, and then maybe summarizing a whole book or something like that. Now, the language model can do that at some level of competency. It doesn't mean it can just do it. Like, the better they get, the more excited we get because they do those tasks better. But that's how we should think about language models. And then, and I've said this, the grammar and syntax thing. Okay. And then the last thing is like parameters. You'll hear about parameters. Gosh, can I explain parameters? So you're going to get to train a language model, or to train any kind of neural network model, you get a bunch of data. And I can't explain deep neural networks quickly to you. I have an idea of how they work, but I'm going to botch the explanation. But the parameters, when you hear about parameters, you should think the model abstracts away. Abstracts from the raw data, sort of the essential features or the essential things that make a difference to the input and output that's been observed in the data, and then once you have the parameters, you throw away the data. This is a parameterized model, and then non-parameterized doesn't throw away the data. But you're always hearing about 1.6 billion parameters or 3 billion parameters. ChatGPT or GPT-3 gets better and better because of the number of parameters that they can pull off. So when you think parameters, you should think training data turns into some sort of simplified representation of the input-output behavior observed in the training data, and that simplified representation is the parameters, I think. Okay. Did I say I'm not an AI guy? Did I say I don't know what I'm talking about? Well, let me just reiterate now. Okay, so now let's go to that graphic provided by OpenAI because I think we can muddle through it. I think we have to, right? We can't talk about ChatGPT and the hypotheses if we don't talk about the graphic. Where is it? No. Where is it? It's right there. I clicked on it. Okay. So this is my annotated version of their raw graphic. So this is their graphic from the blog post about ChatGPT. And I just sort of marked it up and tried to make sense of it. I should have said this at the top. I am not an expert. You should not be getting your AI information from me. Or at least you should not be taking it to the bank. You can get it all you want, but just don't. Yeah. Okay. So first, I think I'm just going to start with what they say. Then I'm going to try and, explain why I say whatever I say. But understand that there are three phases, and that the basic structure of the three phases is first you build something here, then you build something here, and then you put the two things together using this PPO algorithm, okay? So let's start with the step one thing that you build, which they call a supervised policy. When we think of policy, when we hear the word policy, we should think a solution to a complex decision problem. So a decision problem is like, should I do this, yes or no, or should I go here or there? And when those things get sort of to a certain level of complexity, like more and more real-world environments, in a more and more real-world environment, a decision problem becomes complex, and you can't solve it with a set of instructions. You have to solve it with a policy, or you don't have to. But that's what the AI textbooks talk about, is the solution to a complex decision problem is a policy, like a set of rules. So you don't, when you're driving a car, you don't have a bunch of instructions for when to keep right or keep left, depending on what country you live in. If you're driving a car in the United States, your policy is to keep right, except in these situations where you're passing or it's a one-way street or something like that. So your policy is to keep right. It's not when I'm on this street I keep right, and when I'm on this street I keep right, and when I'm on this street I keep right. And you can't enumerate all those. Okay, so when we hear policy, we should think a rule that solves a complex decision problem. So step one is collect demonstration data and train a supervised policy. So let's walk through. So they say a prompt is sampled from our prompt data set, and they give an example here. Explain reinforcement learning to a 6-year-old. Okay, I translate that as a prompt is picked from the data set. Isn't that brilliant of me? How did I extract such sophisticated interpretation from the? Okay, that one's kind of not necessary, but anyway, I'm just doing it all. Okay, I also put extra question marks everywhere where I was like super unsure about what I was saying, but enough. Okay, so we grab a prompt from the data set, something like explain reinforcement learning to a 6-year-old. Next step is a labeler, i.e. a human, demonstrates the desired output behavior. Now, okay, and then I say a human writes or selects a good prompt to response to the prompt. They say here we give treats and punishments to it, so I can't tell what they mean by this. Demonstrating the desired output sounds to me like they write or adjust some given response to this output. Here they're talking about, this sounds like reinforcement, rewards and punishment, which shouldn't be coming in until the training of the reward model. But I don't know. I doubt they made a mistake here. I'm not really sure. But what they mean by this. But the point is to get ourselves started training this policy, this solution to the complex decision problem of how to respond to a prompt. We start by grabbing a prompt, and then we get a human involved to show us, how should we respond to this? Okay. Then we have the data, which is the prompt plus the human demo in whatever form that is. That's the data. Let's think of it as just a pair. These are the input and output. okay, for our deep neural network to observe, so to speak. And the deep neural network, which is, let's call it GPT 3.5, fine-tuned. Okay, so they're saying this data is used to fine-tune GPT 3.5 with supervised learning. And supervised learning is, of course, I turned away from the damn page. No, there it is. Supervised learning, and supervised learning, I'm reading from AIMA 4E now. The agent observes input-output pairs and learns a function that maps from input to output. You should distinguish this from unsupervised, where the agent learns a pattern in the input without any explicit feedback, and then reinforcement learning. The agent learns from a series of reinforcements, rewards, and punishments. Okay, and that's a bit detailed, but let's just say that there are at least three kinds of learning described on page 653 of AIMA 4E. Okay. So let's say that the prompt plus the human, demonstration, whatever form that is, that's the data, and then you feed that into the neural network, and it learns to map the two things together. It learns basically a policy or a rule or set of rules, and it's hard to verbalize this stuff, but you should, when you're picturing it learning and the rules, these are numerical decimal values in a digital circuit. In a data structure that is implemented that is physically the voltages on wires. Okay, so the simplest version would be that our little neuron lights up only if it receives the number 2 or greater. Okay, so an input to that, like each little neuron is like its own little computer or its own little function. And then you just do lots and lots and lots of them, okay? And then you feed, let's say an image, like each pixel of an image into, or some group of pixels or something of the image into these as the inputs to these lots and lots of neurons. And then they have outputs. And then you do another layer and another layer and another layer, and that's deep learning. Again, that's not the best explanation of deep learning, but that's what you should be picturing. But all that's represented as numbers in a data structure. What you're physically talking about, I mean, it's not some contemplative neural network sitting in a chair, smoking a pipe. It's just the data structure, which is really, we should think of them as like little machines or little functions, the neurons as little functions, and then layers of them. And that's implemented. What that is physically is voltages on wires, very tiny wires, like almost, you can't even call them wires. Like there's just like, atoms, chains of molecules or whatever, but it's basically wires. Okay. So that's what we should be picturing. So the deep neural network, this set of things with adjustable numbers, this set of neurons or virtual neurons with adjustable numbers, learns to basically a set of rules, so that when it takes an input to the input layer of the neural network, it can generate the output the same, that sort of matches the way that the prompt seems to generate the output through the human. So if the prompt goes into the human and comes out as the human demonstrating a good response, the GPT 3.5 fine-tuned wants to take the same prompt and generate the same response itself. It's basically trying to learn to be not just one human, but multiple, as all the humans that that are represented, humanity collectively, or the collective of humans represented in the data by the events in the data that it's observing. Okay, so it learns a function mapping the input to the output. It doesn't have to be, now it's crucial, it learns a function. There's more than one. There's always more than one function to map two data sets, two vector spaces together. It's learning one. And that's one of the mysterious and sort of uneasy things about deep neural networks is we never really know how they work, or at least not until we add on things that sort of make, that force explainability, which I don't know anything about, but I've heard that's being done. Okay. We can also think of this function that maps the input to the output as a hypothesis about how its environment really is. And what is the environment? Is it, I mean, in a very, so for this agent program, this deep neural network-based agent program, its environment is, at least so far, it's just what it observes in combination with the prompts and the demonstrated output by the human being. That's its whole environment. That's all it cares about. That's all it doesn't care about. It's not very complicated yet. And so it adjusts the process adjusts it to sort of reflect the way that the environment is. It doesn't. The neural network is not going to survive our engineering of it. It's not going to be preserved and iterated if it doesn't generate outputs that are similar to or close enough to the human demo outputs. Is one way of thinking of it. And then lots of parameters to abstract over the training data, and also the hypothesis is also usable as a program to test itself, to test the hypothesis, because we're using computers. But that's okay, enough. We're taking way more time. Okay, so on this first step, let's say that the data is, just to sort of summarize it here at the top, the data is the prompt and the human selected response pairs. The prompt and response pairs. The policy is a function mapping them, or let's say a solution to a complex decision problem in the form of rules. Okay, that's step one. Let's go over, okay, so get some perspective. So that's step one. We've just sort of trained this GPT 3.5 fine-tuned model, which is trying to be a mapping that is just like how humans are when they get these prompts, or humanity collectively getting prompts and generating these outputs. It's trying to be like that. is a terrible way of saying it. Okay, so let's go to step two. Collect comparison data and train a reward model. So step one is a prompt and several model outputs are sampled. And the way I say this is a prompt is picked from the database, and several of the GPT-3 fine-tuned version N, version 1, version 2, version 3 models, they each generate a response. Version A, I should have said ABC. Version A, B, C. I think that's what they mean here. I'm not sure that they're talking about like multiple slightly differently fine-tuned GPT-3s, but that kind of seems like what this is over here. Okay, and then they all generate responses, and then another human being gets involved and ranks the responses and says D was the best, C was second best, A was next, and B was the worst out of these responses, okay? And then that data is used to train our reward model. So again, we have input-output, okay? We have the input of these responses. So the input is these various GPT model outputs, the slightly different versions of GPT 3.5. I think that's what that means. I'm not sure. I'm very unsure about that. And then the output is the human ranking. And so the next deep neural network we're going to train is going to try and learn a function between these two, in this input and this output. And the reward model is also a hypothesis about how its environment really is. And the environment is these inputs and outputs and the function that it's trying to learn between them. These are observable. The outputs from the models and the human ranking of them are observable. What's not observable is what the deep neural network is trying to. It's so hard not to anthropomorphize, but it's trying to learn, or it is learning by mechanical means, electronic means, but it's not thinking, it's not deciding anything in any sense of the word that we would recognize. Again, lots of parameters abstract over the training data, probably, not 1,000,000% sure. So the reward model learns a function mapping in-out pairs and hypotheses. Okay, so now we have two things. We have basically a chat policy neural network that is pretty good at, it's GPT 3.5 fine-tuned because we're building a dialogue machine here. That's what ChatGPT is. It's not GPT style prompt and then text. It's sort of dialogue oriented. So we have that pretty good, and then we have this second thing, this sort of reward tool that we're going to add to the environment or add to the system that's going to sort of become the environment for this the fine-tuned GPT-3 and an algorithm that connects it to its punishment and reward system. So that's step three. So let's go to step three here. They say optimize a policy against the reward model using the PPO reinforcement learning algorithm. Okay, optimize, we should always think gradient descent. Doesn't mean they're using gradient descent, but that's what we know. We've looked at gradient descent, so it's very familiar to us. If not, go back and check out the videos. We did some stuff. So again, we start with a prompt picked from the database. And the PPO model is initialized based on the supervised policy. The supervised policy is this thing over here. Okay, this and maybe the sort of various versions of it, but I'm not sure which version or where we should point to the supervised policy that's initialized or that's using to initialize. But I'm thinking this is the first step in gradient descent. If we go, actually, can I do this quickly? If we go back to our notes on What word would be there? Great, obviously. But where was that? I have this drawing that is going to help with this. No, I'm not going to be able to find it quickly. The airport problem, maybe. Please get lucky. No, I'm not going to get lucky. Nope. Okay, we'll leave it. I don't want to get. It was late though. I mean, it should be findable. No. How many did I do? Come on. This is going to be worth it. Just stand by. Oh, so close. Is it 6 or is it 7? I'm going to say 7. 7 is the last one. Yes, here we go. See, it was worth it. So worth it. So I'm thinking of the initialization of the PPO model. The PPO is an algorithm, though, is it? Okay. So a model for being used with PPO is initialized from the supervised policy. So this is new, I guess. This is not just grabbing the other thing, the other model. It's initialized in order to be usable with PPO. And I just think of it as like this is our first guess, and we've arranged it in a way that we're going to be able to do gradient descent toward the optimal, so that the gradient is 0, so we make it as good as we can possibly make it. Okay. The next is the policy generates an output. So the PPO initiated policy generates an output. I just said the fine-tuned, FT stands for fine-tuned there, so we don't forget that we're dealing with GPT 3.5 fine-tuned. The reward model response. So the reward model calculates a reward based on this output. So we take this thing. Okay, whoops. We take this thing and it checks the output from this thing, or basically this thing. This is the output here, and it calculates a reward, or it calculates a score or a reward or punishment for the output. And then the fine-tuned policy is updated based on the reward model's response. And then we repeat. We follow this line and we go up and we keep doing that over and over again to improve by using this loop. Okay? And then up here I said to gradient descent from the step 1, i.e. this column over here, the step 1 policy model to the optimal policy model, given the reward model, given this, the PPO, proximal policy optimization algorithm, is used to choose a pretty good step size. The reward model provides feedback, the policy is updated, and the cycle repeats. That's the other thing. The PPO is just sort of, my understanding of it is, I'm not going to try and find a good text on it, but the PPO algorithm is like a good sort of compromise solution to the problem of step sizes. So if we go back to, in gradient descent, if we go back to our little thing here, our little history of gradient descent here, this is the first step size. So this is our first guess, and then we decided a step size as our second guess, and then our next step size is a little bit less. That's a human doing that. That's me making these step size decisions. If this were our starting point in gradient descent and our step size were this long, we would have totally overshot our optimum little valley here, our gradient 0. And then what? Okay, let's gradient descent from over here. Oh, shoot, we did the same step size. We jumped over here. We're going to keep bouncing back and forth. And actually, there's a really cool, okay, hang on a second. Can I find this? Oh, man, I can show you. What can I show you? Oh, darn it. There's a picture of what this looks like. Stay with me, because you're going to love this picture if I can find it quickly or slowly. Either one, you're going to love it. And it's online. I can show it to you. I don't know if I can show it to you. It's, gosh. Come on. It's so obvious. It's beautiful. I just need to find it as a citation once I find the page, and then I can click it through. Gosh, I just have, when I have it open. What is it? Mel book. Okay, math for machine learning, yes. And then take me to there it is, okay. And then the PDF, yes. And then step size. No? Kidding me. Gradient descent, yes. This is not behaving like no, it is. It's behaving. Come on, show me the picture. There it is. Got it. Okay, this is from This is just from, whoopsie, getting too excited here. This is from this book, okay, but it's online, Democratizing Education. This is the step size, and this is, this sort of illustrates the problem. You can overshoot and blah, blah, blah. If you do this wrong, the thing is going to ping pong all over the place. And they talk about that on page 229. Okay, enough. Anyway, so that's what PPO does. Is it's a compromise between step sizes that'll take too long and step sizes that won't take very long, but that might never get you to your target because they're too big. Okay, so that's a way of thinking about what. It's hard to explain. Like I've explained this a couple of times to other employees here at Retraice, and it's not easy. But at least now, when we go talk about the hypotheses, we're not going to be saying dumb stuff. We might not be saying the most accurate, most insightful, AI expert stuff. But the AI experts, they also they have the curse of knowledge. I don't have the curse of knowledge because I don't have very much knowledge. Do you know what the curse of knowledge is? It's when you forget what it's like to not know something, and then when you talk to people about it, it's hard for you to make sense or for them to make sense of you because you're taking so much stuff for granted. I don't take very much for granted, but I also, my explanatory powers are limited here. But we have a good starting point. This is going to improve, just like our companion to AIMA 4E, 4E. Our companion to AIMA 4E is a work in progress, but it's a good start, and it's going to be it's something that we can use. There's a lot of stuff relevant in this too, by the way, to ChatGPT, but that we can use to improve on our understanding. With this in place, with this annotated graphic in place, I feel comfortable talking about ChatGPT and the hypotheses. Not that we're going to give some, school on, a clinic on how ChatGPT works. We just need to have some sort of sense of what it is and what it is or how it works and where it came from and where the humans are involved. I think that's it. I don't think I want to. Is there anything else that in my notes that I wanted to? That's it. Okay, so that's it for now. We'll pick it up tomorrow. We'll cross now the missile with the hypotheses, and same time. No, not same time. 4 p.m. tomorrow. 4 p.m. tomorrow. Yeah. That's it, 4 p.m. Eastern. Okay. This has been Retraice segment number 100. Not the best one, but you know what? I'm happy. And that's it. Of course, the 100th one is going to be kind of iffy. Look, we're not going to even know what we're doing. I've been saying this internally and thinking it myself. We're not going to even know what we're doing on this podcast until we get to 1,000. Why do you think I'm doing them every day and multiple times a day? Because we got to get there. We got to get to 1,000. Okay. That's it for now. Not same time tomorrow, 4 p.m. Eastern tomorrow. Signing off.